Thanks for joining us for this fourth video in chapter 11. I think it's the third in the IR series. Okay, we're gonna actually try to look at how we can tackle some problems or like identifying functional groups as well as identifying what kind of compounds we have based on the IR. And again, I can't stress this enough. This one diagram, one graphic here is really important. Single bond to hydrogen, triple bond between two big atoms, double bond between two big atoms. Okay, those are the regions. The wave numbers matter, right? Now, can we solve this problem from, this is I think from another textbook. We want to know what kind of compound we have here based on the IR spectrum. So one of the things that stands out, of course, is this carbonyl, right, at 1720 wave numbers. And then we see that there's these interesting two peaks, 2700, 2800. That's very indicative, very diagnostic of something. And then before I say what it is, I hope you have the functional group in mind. And then on top of it, right, like you have this peak, which may look like an NH peak to you, remember, but when you have a carbonyl peak, really strong carbonyl peak, often there's going to be an overtone at the wave number about twice the strong signal that you have. But you could think of it as like as an echo of a really strong signal. And then I didn't circle it, but of course we have these sp3ch stretches here. So all of that combined, does it make sense to you? This is an alkyl aldehyde of some sort, right? These three peaks combined tell me that we have an aldehyde. Remember, these two come from the unique CH bond in the aldehyde, and then these bands here tell me that there's quite a bit of alkyl present. So alkane chain and an aldehyde in the end. Something like that is this compound. Now, of course, IR alone, there's a limit to this, cannot determine the exact structure. Like in the previous problem, like I couldn't tell you how many carbons you have in that alkane chain or anything like that. Some signals can be somewhat ambiguous, so it takes a little bit of practice and experience to interpret it rightly for sure. Usually IR, what it's good at is indicating what functional group or groups you have. And the absence of a signal is often considered a fairly good evidence that that particular functional group is not present. If you need to determine the exact structure, you often need to compare with the known sample of that same suspected compound. Hopefully you have a standard in your lab, and you have to compare the two IR spectra to be sure. Often it's still then a little bit ambiguous, so and that's part of the reason why we need a little bit more powerful techniques like mass spectrometry and NMR that we're going to talk about very soon. One of the main things we want to do during class time is to practice interpreting IR spectra in the IR practice packet, which should be posted online. There's two parts to it. There's the known spectra, and in those known spectra, I want you to identify the prominent IR bands that correspond with functional groups or specific chemical bonds. And then in the unknown spectra section, I want you to match the compound structure with each of the spectra. Okay. We'll post answer keys at some point. But before we get into that packet, I just want to show you an example of matching bonds you see in the known structure to each of the prominent bands in the IR spectrum. Okay, so here's what you would do. So here's a particular molecule. You see the alkyl group here, right? Or I should say there's an sp3ch stretches should be present in this methyl group. And remember, one of the things you should do immediately when you interpret an IR spectrum, draw a sharp line at 3000 wave numbers. And that's very useful for telling whether you have that sp3ch stretch, which should appear right before 3000. And then, of course, we have this OH group, which is not a typical alcohol because this alcohol is very acidic, kind of like carboxylic acid. But nonetheless, it's fairly regular-ish OH group because it's not as, yeah. And so this shows up around usually 3300. This is showing up around 3200. One of the reasons is this is a more acidic OH than regular OH because of the resonance of the conjugate base. If you took that proton off, the negative charge would be conjugate, resonance stabilized, and so forth. So there's that OH. And of course, the most prominent is going to be this carbonyl. I want you to notice the wave number is slightly less than 1700. And again, that's because of the conjugation that we talked about last time. And then this falls into the fingerprint region, so I don't need you to be able to identify it. But the oxygen carbon bond often shows a strong peak around 1100 or 1200. More importantly, around 15 to 1600, we see the CC double bond stretches. So altogether, that seems to be the right spectrum for this. The bottom is a spectrum that a student acquired in an Chem class. I want you to notice that the wave numbers pretty much match up, but some of the appearances may look a little bit different. And also, depending on how you prep the sample, each signal's intensity may be a little different in each spectrum, so that's something to be aware of. Now, let's get into the sample packet. I want you to take a few minutes to actually try to do this on your own, matching the structure to the spectra for the known spectra portion of the packet. And then I want to go over just a couple with you here in the video. The rest of it we'll do in class. Okay. Here's a compound actually known as acetophenone. It smells like a pistachio because this compound is actually present in pistachio. But here's the carbonyl, which shows up here again. It's lower than 1700 because of the conjugation. So that we could identify that as carbonyl. And we should see sp2 alkene type CH stretches, and then indeed we see that right after 3000, a little bit above 3000. So those are sp2ch. One thing we forgot to do, we didn't draw a sharp line at 3000, so let's do that. Why? Because we do have sp3ch bonds in this structure, so we should see that right before this 3000 line. Unfortunately, it's just this little blob. I don't know if you can see it, like in the shoulder of the other peak, there's an overlap. That is sp3ch. All that to say, like sometimes some of the signals are not as strong as we hope to see. Also, there can be like these artifact peaks, like this overtone peak that is a result of that carbonyl signal. There's known spectrum B as this structure. Let's see if we could identify the bonds. If you haven't, I would encourage you to take a pause here in the video and see if you can do it yourself. This time I didn't forget to draw that 3000 line, okay? Now, this area around 1600 something should be indicative of carbon-carbon double bonds. Now, some of you would be wondering, well, isn't that the same area where like a conjugated carbonyl shows up? So how do you know? Again, this is sort of where the ambiguity of IR interpretation comes in, but one way you know that this is not a carbonyl is it's not a very strong signal. Carbonyl stretches are always very strong. It's usually the tallest peak there is in the spectrum. So this is likely carbon-carbon double bond. Now this very unique wave number. It should be for triple bond, and indeed we have a triple bond nitrile in our structure. These peaks are right before 3000, 2900 something. That should be indicative of sp3ch, which we do have because we have this methyl group and this methine CH. Right, and then past the 3000, we should see the sp2ch, which we should see that because we've got all these sp2 carbons. So we've been able to identify these four prominent bond types. Now to the unknown spectra section. Again, please finish doing all the known stuff during class. This is just to get you going, primed for the class practice. Again, it's a good idea to draw a line at 3000. Right before that, we see these peaks, likely these sp3ch. And then we don't really see anything else. And this, do you notice this like overly clean spectrum, as in like there's not very many signals bands, right? And that is because this belongs to this polymer. If wasn't super clear to you, this like bracket with an N, that means this repeats N times, like many times, right? Like this CH2 just goes on forever. It's basically a really, really long alkane chain is what this formula is showing. Now, this is a polyethylene plastic. It's a polymer. It's made from ethylene, CH2, ethylene molecule polymerized by a radical reaction typically. And this is what the IR spectrum looks like. Now, the reason why the spectrum looks so clean or like very few peaks is because it's a polymer, all these CH bonds and CC bonds are embedded in this super long, big molecule, so they don't have very much of a freedom to move around. So there's only a few dance moves, so to speak, that they can do, and hence very few signals. That's typically an indication that you're looking at a polymer. Here's unknown spectrum number 1. See if you could identify some signals that would be important. Again, get in the habit of drawing a line at 3000. Right before that, we see some peaks or signals, likely these sp3ch. This looks like an OH signal, broad OH, but it's overlapped, so it's a little bit ambiguous. I'll leave a question mark there. This definitely seems like a place where only the triple bonds or sp bonds show up, so tentatively I'll assign this as alkyne because the signal is not very strong. Usually nitrile C and triple bond is pretty stronger than that. And then there's a sharpish peak here. Now, this could be like NH perhaps, but another possibility is SPCH, which is consistent with the fact that we're suspecting to see alkyne, right? That's SP. So if this is a terminal alkyne at the end of a chain, there should be a SPCH bond, which shows up around this wave number. So that's likely the assignment. Now, that's great, but one thing you might notice is this looks exactly like the unknown spectrum 5 with some differences in the fingerprint region. All of that to say, the unknown spectrum 1 and unknown spectrum 5, they both seem to have the exact same functional groups. And in fact, you might have noticed in the pool of structure candidates for the unknown spectra, there's two compounds that are very similar. Both of them have alkyne, terminal alkyne, and an alcohol on the other terminus or the other end of the chain. The only difference is the metal alkyl chain length, right? These two you really can't distinguish by IR because they both have the exact same functional groups. If you need to distinguish these two, you're going to have to do other analyses like mass spectrometry or NMR spectroscopy. That's kind of the point we wanted to make with these two spectra. Okay, so here's spectrum 5. Notice the very similarity, right? By the way, this 5 is actually this compound, and spectrum 1 was that compound. But again, you couldn't tell between the two just from IR. Just saying, like, unless you have the known spectra of both of these, then you could compare the fingerprint region, but we're not going to require that in our class. So again, just the summary of IR strength and limitations, because in a little bit, you're going to be, very soon you're going to be determining the structure of completely unknown compounds using IR, mass spec, and then NMR. And as you use those three tools, analytical tools, I want you to be aware of the strength and limitations of each analytical techniques. Okay, so I'll see you in the next video where we're going to start discussing mass spectrometry.